corner we have Chris, who's risen to the challenge and he's going to shout. He doesn't want a mic, so we'll see how we go. Okay, are we all ready? Over to Chris Hausler, who's now going to put the case for Python. And then after this we'll have a joint Q&A. Finish the beers and head down the pub. So, thanks Chris.
Hi, I'm Chris. So, the title of my talk is Why Pi. I have to thank Andrew for the idea. He came up with YR, and I thought Why Pi would be Y better. So I think we're already one step ahead. So I am a data engineer at Zendesk. We are like a software as a service sort of thing. I have the honor of working with a bunch of really smart people, which is awesome. I've been using Python in academia and in the industry for about 8 years. Before that, I had the misfortune of using MATLAB. I don't know what else I was going to say about that, so I guess we'll just get to it. I pretty much wrote the same talk, so if it looks familiar, it's because we cover almost the same things, except this one's in Python. Alright, so I thought the first thing I should tell you, actually before that, if you can't hear me, let me know, I can yell louder. Also, if you've got questions or you feel like heckling, just yell out. So Anaconda, despite their awful logo, is a really good place to go and get Python if you're just starting out. So Anaconda is like Python with a bunch of prepackaged libraries. So Python has like the idea of libraries like you see in R. So if you want things, you can go and get other people's code that does that stuff. Anaconda comes bundled with like 150 packages, libraries of things that do stuff that you probably want to do. So specifically, they say they are free enterprise-ready distribution for large-scale data processing, predictive analytics, and scientific computing, which sounds pretty much like what everyone here is interested in doing. So it's a good place to start. Alright, so I'm going to talk about these 5 things in order, which is basically what I want for my data stack, right? So if you're doing data analytics day to day, you're building models, you're trying to find insights, there's a few things that you want to be able to do, right? You've got to do munging. You've got to be able to read in your data and turn the crap that comes in into something that's usable for the thing that you want to do. You're probably going to have to plot it because without looking at your data, you're not going to know what's happening. You might want to do some learning because maybe once you've looked at your data, you're like, maybe I can predict this from that. That's kind of the exciting part. And then there's a couple of other things that like come up sort of maybe in my job now more so than previously, which is productionizing. So how do you turn that into something that is actually usable not only by you, but maybe by your company or maybe by some website or that gets passed off to millions of end users or something like that. How do you make it scale? And how do you collaborate with it, right? How do you show other people the cool things that you've done and make them understand what it is you did and maybe be able to reproduce that? So they're the things. I'm going to start with munging. Specifically an introduction to a library called Pandas. It's got a cute name. You start it like this. Is that readable? Is that the font big enough? Cool. Okay, so importing a library in Python kind of says what it does. Import pandas as PD. So it's like, I want to get pandas and I want to call it PD so I don't have to type pandas all the time because it's too many letters. Pandas gives you a thing that you will be familiar with from the last talk called a data frame. It's almost identical. Here's some toy data. So I created a data frame called ages. It's like, when I put it, it's like a list of lists. Basically, it's a whole bunch of like pairs of things. So John 25, Mary 9, Radek 16, right? And we get out something that looks like this guy down the bottom, which is effectively an array. So you've got rows and columns. But this guy is not very interesting. This guy is exactly like an array. You get arrays in Python as well. Data frames are nicer. And the reason data frames are nicer is 2 things. One, you can have multiple types. So you can have strings and numbers together. They live happily in data frames. They don't live happily together in arrays. And the other thing is, which I haven't done here, is that you can name your columns. Because this data is easy to look at. When you've got a million columns and you're trying to remember which column was age, whether it was 2,356 or 57,512, it's kind of taxing on the brain, right? So what you want it to be able to do actually, you want to create a guy like this, where you can name the columns, right? So we take the ages thing from before, we call ages.columns, we set the column names to name and age. And then I tell it, okay, and then set name as the index, right? So now we've got a label for our column, which is age, and we've got labels for our rows because I've set name to index. So each row is named after a person, and you can ask for the column. So I can ask for like, give me the row that has John and give me his age. And you will see that on this line, right? So we can use the index, so we can ask for ages, give me back John and Mary, right? And we get back like another data frame, which is a subset of the original data frame we had. We can ask for things that don't exist, like give me John, Mary, and Thomas. Thomas wasn't in there. So you get Thomas back as a row, but you get something that we saw before as well, called an and, which is not a number. So Python also has a way of telling you when a thing is missing, without it just being blank or being a zero. It's a special type of thing that is not anything, really. Which is useful, because you want to know when things are missing, so you can fill them in with something that you guess. So data frames do basic arithmetic. You can multiply them by stuff. Ages by 2 makes everyone twice as old as they were before you multiplied it by 2, which is useful sometimes. Okay, so we've got one data frame. We can create another data frame. We'll call this one genders, right? So you can specify the index and the column names in the creation if you want. So that doesn't have to be something you do afterwards. So here we're saying this data frame has male, female. The indexes on the rows are John, Mary, Alberto, and Karen. And the column's called gender, right? So everything that looks like the guy before, but this one has gender in it. And it's got some different people. Some of the same people, some of the different people. So a cool thing that you get with data frames, and I think this is like the sort of the winner for why you would want to use data frames in Python over arrays, is that you can do things like joins. So if you're familiar with SQL databases, you can think of data frames like a database table. And you can join them together. You can do left joins, right joins, outer joins. They join on their indexes. And so we can take data from 2 disparate sources, which is often what you want to do, right? A lot of the time you'll have data that comes from over here and from over here and from over here. You want to stick them all together. Pandas does that for you. You just like set the indexes to be the things you want to join on, and you go join, and then you get the guy that's join. And it manages things like, okay, so we're doing a left join here, so people that are in the gender data frame and not in the ages data frame get an and, right, for their age, because we don't have an entry for that. But people that are in both, we get a nice join, and we know things about them. So far, so good. I should have said at the beginning, I'm going to like power through like, well, not a billion things, but lots of things. I don't really want you to be able to like, at the end, don't feel like you need to like understand all of the code. First of all, it's on GitHub, so you can just go and look at it. I'll share a link. And the other thing is, I just want you to have like a feel for all the things you can do and how easy it is to do them, right? Like, you can Google the details. The documentation's good.
Let's join.
All right, so missing values. We have some of these now, right? Our data frame called people has a missing age for Alberto and Karen. So what can you do with these missing things, right? The easiest thing is to tell them this off. Drop an A, they go away. It's like it never happened. Good, right? That's the first step. But sometimes, like, you know, in the case of tree heights, you can't throw them away. You need to fill them with something. You might need to make an estimate of what the tree height might have been. Choose some number randomly out of the sky. In this case, we can do something like, okay, let's fill it with the mean of the age of people. So here we're calling people, give me the column age, grabbing the mean of that, and then fill the missing values with that number. And so those people become 17. So that's one approach. It has other things like forward fill, which basically says just, if there's missing things, just keep copying the last thing you saw until you see a new value. That makes everyone 9. I don't know if that's good or bad. Okay, so that's toy data. Toy data is boring, but it gives you like an intro to what data frames look like. But you want to load data from the real world. Pandas speaks many languages: CSV, Excel, HTML5. It can talk to SQL databases. It can read JSON. It can read from your clipboard. It can read HTML. It can read lots and lots of things. And any of the things it can't read, you can very, very easily write your own reading thing for it. Right? It'll read anything that comes back as a list. So that's useful. So we should load some data. We're going to load some data called pedestrian count. This comes from the Melbourne City data website. Melbourne City has like an open data thing. You can go there, and it has mostly boring data sets, but this one's kind of cool. It's basically from years 2012 through 2014 for a bunch of places around the city. Every hour of every day, how many people walk past it. Kind of cool. This is a subset of it. It's 3 bridges and 3 railway stations. So what you see is like, you know, rows of the time, you get the date and the time. Pandas knows about date times, right? So you can set date time indexes and you can slice by date time. You can say, I want all of the things from July in 2012, and it knows what that means, which is very, very nice if you're dealing with time series data, which comes up a lot in life, I find, in my life. Interesting things to note when you look at this is that Flinders Street Underpass and Princess Bridge, which are both ends of Flinders Street Station, are very popular at midnight, like New Year's Eve in 2012. Flagstaff Station, less so, probably because it's closed. Okay, so I didn't mention, we've loaded that, we've stuck it in a guy called Data. You can call a thing like data.head, so data frames have things you would be used to from Bash, if you're like a Linux Mac sort of person, head, tail, that sort of thing. Get back the first 10 rows, first 20 rows, last 10 rows, whatever, right? Okay, so we can ask our guy Data for data.info. This will look really familiar because there was a very similar slide in the outlook. It tells you, these are my variables, right? We've got web bridge, princess bridge. How many values are in there that are non-null, and what data type are these? These guys are all floating points. I don't know why, because we could just log in into the data. Sorry? Oh, this guy? That's how many rows there are. Sorry, there's lots of rows. Right, so that's how many data points you get when you look at 2 years of data every hour. So now you know how many hours there are in 2 years, or 3 years. Okay, so you can call info. You can call describe, which does like, with lots of decimal points, does basic statistical analysis on all of these problems. So it gives you like count, mean, standard deviation. The minimum, the maximum, 75%. You can look at that and say like the most people in any one place in 1 hour was at Flagstaff Station, because that's the biggest number. So it's a good way of just like going, I loaded some data, I don't know, what's in there, sort of. Right? So that's the end of my introduction to data frames and introduction to like sort of munging. There'll be more stuff coming, right? So the next stuff is plotting. Because generally at this point you're like, okay, got my data, kind of know what it looks like, maybe we should look at it a bit more, make some pictures. I'm not very good with numbers, so pictures are good. And it's got some more advanced pandas operations because you might want to summarize your data in certain ways before you visualize it. Okay, so plotting in Python. Python's main plotting back end library thing is probably matplotlib. Pylab is kind of a wrapper on that, I think. I always get confused. So I always import Pylab. I don't know why. I think you can just do import matplotlib here, and basically the same thing. I can't remember what it is. So that's your plotting library. Guy under it, Seaborn, is a thing that takes matplotlib and throws away its ridiculously ugly defaults and makes plots pretty ugly. And then you set context. So it's got a thing where you can like tweak the defaults that you get in plots. It's got context, it's like talk, poster, paper. Funnily enough, poster works better for a talk than talk does. I should write them a letter, I don't know. So, okay, so we can start plotting things, right? Okay, so we can create a data frame called bridges where we go to data, which we loaded before, and we get the columns that are web bridge, princess bridge, and sandwich bridge. So that's a new data frame. And then basically the line that plots all of this is this. Bridges.plot. That's basically all you need. You might tell it how big I want the figure to be, but that's it, right? So pandas data frames know how to plot themselves, which is super useful. So you get the, you get the legend for free, you get the x-axis label for free, it knows how to deal with dates. The only fancy thing I did there is tell it that I want it to be that big and that I want to set the y label be pedestrian, number of pedestrians. So you can tell two things from this plot. One, that if you look at 2 or 3 years worth of data at hourly sample on a really small plot, you can't really tell much about what's going on at all. And 2, the web bridge is either plotted behind sandwich bridge or missing. So you probably need to do something else to get a better feel for what's going on there, right? So we can do that really easily. We take the bridges data we had before, and we call resample, right? So data frames know about dates. This data frame has a date, has an index, a date time, so it knows how to resample. So I tell it to resample by day and to sum up the things. So what that does is it takes all of these hourly things and goes, squish, give me one number per day, per place, and sum up all of the hours that are in that day and give me another one, right? And when we plot that, we get something that's a little bit more useful, because now instead of having 24,000 blah data points, we have, what's 3 years, like 1,000 data points. Suddenly you can see a little bit more information there, right? Like, Princess Bridge is by far the most popular. It has some spikes at certain times of the year, specifically around January, I don't know, Australian Open, New Year's Eve, who knows. The other bridges are kind of neglected, right? So it's pretty easy to sort of start manipulating your data and summarizing it, rolling it up by, like, by periods that you might be more interested in than hourly, right? So you can resample very easily. Say we want to split that out, right? We don't want to plot them all together. We do the same thing as before. This is now rolled up by month. So you can see every sample is M. So it's basically the same as what we did before. But the only difference is we call subplots equals true. Now we get each column in a different subplot. You get back handles to all of these things so you can tweak them and change them as you please. I don't know. This data is like just filler data. I can't tell you anything exciting. Yeah, that's it. Moving on. Okay, so maybe you have a question, right? Like, tell me the median pedestrians per hour at Flagstaff Station in July 2014, because I know this is a question that everyone is interested in. And if you woke up one morning and you thought, I have to do this, this is how you would do it, right? Like, you would go and you would say, I want a new data frame. Here I'm going to call it DT because descriptive names are good, right? I'm going to get data, I'm going to index in there, I'm going to tell it I want things from 2014-07, right? So it knows that it needs to be things in July 2014, and anything else after that, like from the 1st to the 31st is fine. But in principle in there, you can put 2014-07-01 to 2014-07-05, or whatever you want, right? It can slice things, it knows how to sweep it. Okay, so we get that. That's our DT. So then we go DT, group by the hour in the time. So this is like a SQL group by, right? So you're saying, hour in the time is like what hour of the day was it? Was it 1 a.m., 2 a.m., 5 a.m., 10 a.m., right? So group all of the day, all of the measurements at 5 a.m. regardless of what day they were together. Give me a number, right? Give me the median specifically, because I asked for the median. And then plot it. And then give me a bar plot and the figure size. And you get something like this, right? So you can see, for example, that if you want to avoid people at Flagstaff, you probably get there just after it opens, somewhere around 5, definitely not between the hours of 2 and 3. And in the evening, you should probably go home around 6 or later. So it's pretty easy to sort of roll up your data. Oh, because there's no people.
7 to 8, 7 to 9.
So 7 to 9 is busy.
If you want to avoid people.
If you want to avoid people over here, where there's no people.
And the station is closer.
They won't let you in, but they won't give you anything. Okay, so that's like, I'm just going through all of the plot types you might want, right? This is not very, it's not very informative, but hey, you'll be able to see at the end that like you can do all sorts of different plots and they're pretty easy to do. And actually Pandas knows how to plot itself for all of these plots, right? So this guy's box plot, right? Resample everything by day and then give me a box plot. So that's happening here. All of the other stuff is like set labels, so switch axes, whatever. So basically this box plot is like a distribution of how many people there are per day at a given place over the last 3 years, right? You can see things like Webbridge is still very unliked, but consistent compared to Flagstaff Station, which has peaks of popularity and lows of being very well ignored. Again, very simple to get like all of your sort of standard plots. There's not anything there that's really more than one line. The plotting pool, there's no more than one line. You can do slightly fancier plots, right? If you want to do a scatter plot, we can step out of Pandas. Pandas knows how to do a scatter plot, but C1 does prettier plots in general. If you're interested in pretty plots, you should go and check out the C1 gallery. It's like, it's good. If you're into data visualization. Okay, so this guy's pretty easy. It's called a joint plot. You're asking for a scatter plot. So we pass in the data over here. We say, we want these two columns, Princess Bridge versus Flinders Street Underpass, so they're the two ends of Flinders Street Station. Show me how many people turn up. Scatter plot it against each other. You get nice marginal distributions on the side. I don't know. I put this here for no other reason than I think it's pretty. And I think that brings me to the end of the plotting section so we can get on to the more interesting stuff, which is machine learning. And an introduction to scikit-learn. So, Python, unlike R, you can go to one place to get pretty much all of your machine learning libraries, and they're all pretty good quality, all very good quality, I would say. More specifically, if you want an SVM, you don't have to search for a library called E1071. Although, wait, forget that! I know it. There's going to be one thing I can do in R, it's going to be importing that library. Okay, so scikit-learn, right? Scikit-learn is a package of machine learning. It comes from INRIA in France originally, research lab associated with universities. I think it's like CSIRO for here, or more like Nicta or something like that. But anyway, it does pretty much anything out of the box in machine learning that you might want to do unless you're after very specific algorithms. It does classification, it does regression, so supervised learning covered, unsupervised learning, clustering, dimensionality reduction. I think on like doing this picture from Andreas Muller, I think it's like this. I don't know. You should look it up sometime. It's kind of like if you're starting out machine learning and you wanted to think like, I don't know where to go, you can just kind of follow the dots, answer the questions, you'll get to the algorithm that might work. Okay, so different data set. Given that it's like the 1-year anniversary of when Jeremy Howard spoke here, I figured I would steal some data from Kaggle. And this is from the Titanic Data set from their, like one of their machine learning competitions. Basically, the point of this competition is you know stuff about people who were on the Titanic and you need to predict whether they died. It's kind of morbid, but, well, the columnists survive, so it's the optimistic version of that, but you're effectively doing the same thing. Okay, so we load the data set, we drop some columns, not interesting. A couple of things you'll note about this, right? So we've got rows that represent people that were on the boat. We've got columns that represent things that we know about them. Two things to note if you want to throw this in a machine learning algorithm. One is that we have text, right? We've got the gender, sex, we've got the cabin that they were in, we've got where they embarked from. These are letters, not numbers. Machine learning algorithms do not like letters. So we're going to have to turn them into numbers at some point. The other thing is that we have missing values. So like cabin, we've got a nan, right? So we don't know what the value is there. We're probably going to have to fill it with something because algorithms like it better when you fill it with things. So we can start doing that sort of stuff, right? So not only does scikit-learn offer good machine learning algorithms, it offers good pre-processing algorithms. But before we get to any of that, let's just clean up some features and make some new ones. So we can create a new feature called alone. So there's two columns, one called parch, which apparently stands for parent and child, stuck together in an incomprehensible half word. And sibs, which is siblings or spouse. So they count how many of those people were with you. So you can check whether someone was on there alone by adding up those numbers and seeing if it equals 0. So if they weren't there with anyone, both of those numbers are 0. Okay, that's like a feature, right? Like, was the person alone? Because if you're alone, you kind of don't have to wait to help someone else off the boat, right? You can just run for the lifeboats.
There's no one to help you.
Okay, other things are like cabin and embark. So we can just fill those, instead of being nan, we can fill them with a string called NA, right? So we still know that they're missing, but it's a string, and later when we go and use a categorization algorithm, we can just say that's a category. It's a category where we don't know about it. Fine. Age is a little bit more difficult because putting a 0 there is kind of misleading. Putting 100 there is misleading. Putting 9,000 there is just going to screw your data. So I don't know, I just thought fill it with median. There's no scientific reason behind that outside of it's easy. And so we get a new version of this data set where it's a little bit cleaned up. The nans are missing and there's no missing ages. And we've got the new alone thing. Okay, so we want to go and throw that at an algorithm. First, we might want to have a look at the data a little bit. This is called a factor plot. It's using Seaborn again. Look them up. They just give you nice plots out of the box. Okay, so what you see here is for the passenger class 1, 2, and 3, and for male and female, what your survival likelihood was. So if you were a female in class 1, you were very likely to survive. If you were a male in class 3, you're pretty much doomed. It's not, you could tell this if you watch the movie Titanic, it's basically the same, right? Kate Winslet, rich, survives. The DiCaprio, poor, does not survive. And that's the data points in between, right? So it tells you maybe there's sort of interesting features, like the class that the person was in, and their gender, maybe their age is also like an influencing factor. Okay, I just put that in there for
What does the red lines mean?
Oh, which ones?
What are the red lines?
Oh, these guys. They're confidence intervals. So the factor plot in Seaborn does like bootstrap sampling thing and gives you confidence intervals out of the box once you tell them. Which is kind of useful, I guess. Although it depends, right? It depends on the message you're trying to tell. Like if your data's shit and you don't want people to know that there's bad confidence. Alright, so we want to build categorical features, right? We need to take things like where people left from, the strings that are like C, Q, and S. They stand for a city. I can't remember what they were. And so machine learning algorithms don't like letters. They want numbers, right? So one of the standard ways of turning this into numbers is to make like effectively like a bag of words sort of thing, right? So we've got 4 different starting points. So we'll give them 4 columns. For each person, we'll put a 1 in the column. of the value that is of interest, like the place that they started from, right? So first person started from S, second person started from C, third person S, and so forth, right? So that's really easy. So scikit-learn has a well-named part of it, a module called pre-processing, and from that we import a label binarizer. And it does basically what it says, right? We call label binarizer.fit Titanic.embark, so where they embark from, so fit that information. So the thing learns basically what categories are available. And then we just tell it to do a transformation and we get that guy out, right? So it's learn about what categories are there and then turn it into like a grid of numbers that we can throw at machine learning over.
Why don't you do linear 1, 2, 3, 4?
Because there's no linear relationship between them. If you label them 1, 2, 3, 4, a linear classifier is going to think that 4 is kind of better than 3, right? But there's not really any relationship. It's just they're disjoint. So if it was a numeric feature, you would. But here you kind of want to separate them out. I mean, that said, it depends on the algorithm you use, right? Some can deal with that, others. Okay, so that was doing one column. We can do them all at once. This is kind of a similar thing to supply, I guess. It's like basically a loop without doing a loop. It's called list comprehension Python. So we create a label binarizer, right? And we say, for every column in this list of columns, get that information out of Titanic and do fit transform on it. So basically go through cabin, embarked, and sex and turn that into those things that we saw on the last slide, right? So you can do that in one line for all of them. It's H stack just stacks them horizontally, so 6 them together. So we end up with basically an array that's like 153 columns wide that represents like the categorized version of all of that data. Okay, so we're pretty much ready now to like grab that and start throwing it at an algorithm. So our data set is effectively this, right? Our Y is whether they survive. So that's the thing we want to predict. Our X is the joint, like the concatenation, if you will, of getting the numeric data out of Titanic, so the things that were already numbers, and the categorical data that we created on the last slide. Stick them all together, then we have like numbers now that represent people that we can throw into the thing and work out whether they survive. And doing that is as easy as this, right? We import some things. Cross-val score. This does cross-validation scoring on a classifier for you just as a function, right? So, the classifier we're going to start with is stochastic gradient descent. So we create our classifier here. So we want to use a logbox function, but that's kind of just ignore that for a moment. Create a classifier, right? Out of the box, default parameters. And then we go cross-val score, pass in the classifier, the data that we're using to predict, the data we want to predict, how many times we want to cross-validate. Does everyone know what cross-validation is? Is that a yes or a no? Sorry.
I used it.
Okay. And how we want to score it. Like in this case, we're using accuracy. It's probably not the right metric for this. It's unbalanced. That's what they use on the competition on Kaggle, so we'll stick with it. It'll give us a number, right? So we put the stuff in. We say, go and do cross-validation magic. Come back. What you get back in scores, which we're assigned to over here, is a list. So for each of the 3 conscious validation runs, what our accuracy was, right? And we can calculate the mean on that, and we can say that's how well the model does, give or take. And it does terribly. It's 0.54. That's close to chance in a balanced data set. It's not good. Okay, how can we do better? Well, classifiers have other parameters, right? Things like, in the case of a stochastic gradient descent, this guy alpha. Alpha is like a regularization parameter. It tells you basically how much you want to like constrain your weights in the model so that you don't overfit your data. That's basically it, right? So you can set that to any number, any floating point number. So what's a good one? I don't know. History would tell us something between like 0.00000 something and like 100 is probably in the realm of possibilities. So we can go through a bunch of them, right? Like, so we have a list of numbers, we go through, so for each of these numbers, we assign it to the letter A and we say, create me a classifier where alpha is equal to A, and then do the thing that we did last time, and then print out the results, right? And you can see that as we change the alpha, we change the score, and this guy here, that looks like a win, right? Like 0.71, we've jumped 20% in accuracy, which is, I don't know, that's kind of cool. Like, given that we've added the whole, effectively, 1 line of code, we're making progress. Can we do even better than that? Okay, so parameter search is a big deal, right? When you're trying to tune machine learning algorithms. Algorithms tend to have lots of parameters. A thing that I won't go into here, but is a thing, is you can build pipelines in scikit-learn, which is effectively not just like using just using stochastic gradient descent to fit your thing, to fit your model. But you can chain that together with maybe normalize the data and then do PCA on the data, and then maybe join that together with the inverse of itself, and then do polynomial feature expansion, and then take all of that and throw that at a classifier. And then the classifier itself has like, I don't know, 5 or 10 argument parameters that you might be able to tune. So that's a lot of things that effectively you're kind of guessing at the beginning. You might have an idea of what like a good starting point is, but it's kind of tricky, right? So how do you choose a good one? Well, you don't. You just ask the computer to choose one for you, and that's much better. So it's got a thing called randomized search CV. So this is like, if you're familiar with grid search, the grid search is effectively like make all possible combinations of those things, try each one out, and find which one's best. Randomized CV search is like, I'm too lazy to do all of that work. I'm just going to do it like n times, and I'll tell you the best out of that. We'll just sample randomly, right, from the parameter space. So we can set up and we can say, like, we want our alpha to be, like, we take 50 samples in this log space. It's like just a bunch of numbers. We might want to try different loss functions, log, modified Hoover, maybe perceptron. We've got 2 different types of penalty for regularization, L1 and L2 norms. And maybe the number of iterations we want to run our algorithm for is different, right? 50, 100, 200, right? So we set up the parameters we want to search for, and we create our classifier like we did before. And then basically we just say, randomized search CV, here is my classifier, here are my parameters, find me 100 things, start 4 jobs, do it in parallel, because my computer can handle 4 but not 5 jobs. And then we do a fit on that, and you let that run, and when it's done, it spits out, you can almost see it, down the bottom, it basically spits out, like it goes, alright, so 3 folds, cross-validation, we need to choose for 100 things, so we're going to do 300 fits. We'll go and do that, and then I will spit out at the end the best accuracy that I found and the parameters that match that accuracy, right? So we get back 0.78. This is like almost 30% better than where we started, so this is kind of cool. And it tells you the parameters. The magical alpha number is 0.01325711365590181, so don't forget that. So, I mean, this is why it's good to ask the computer to like, sort of optimize this stuff for you, because you would never come up with that number. To be honest, if you like trimmed up a few decimal places, it probably wouldn't. Okay, so it's very easy to do parameter search, and that's often something that you spend a lot of time having to do when you're building these sort of models. Okay, but so this is like a similar question to what was asked in the last talk. Is okay, what about different classifiers, right? Maybe I don't want to use stochastic gradient descent. Maybe I want to try random forests. I want to try whatever, right? Like decision trees, Ada boost, Gaussian naive Bayes, logistic regression, k-nearest neighbor. We can just import all of them, right? And we'll make a list of them, and then we'll just try them all out. We'll see which one's best. So these are all, these guys are just initialized with their default parameters, except for a couple that aren't, because I don't remember why. But the point is that you could do the parameter search on each one of these individually, but just to make a point, we'll just create a list of these and we'll fit all of them, and we'll see how they do it, right? You'll notice the nice thing here is that instead of importing different libraries, they all come from the same library. They're nicely named, like the linear models come under sklinear model, and the trees come under trees, and the ensembles come under ensembles. And naive Bayes are under naive Bayes. I won't make a point. Okay, so to train them, it's a loop. For each classifier, we think that we did a million times, right? That's nothing new there. We can make a graph with a fancy choice of colors. It basically shows you how many of these are, right? And the numbers aren't very important, although it seems that like logistic regression around forest do okay. But none of these are true, right? It's just sort of throw some stuff in, throw the data at some stuff and see what happens. But the point is that it's really easy to do that, right? So when you get your data set and you're not entirely sure what, academically speaking, the right model is to use for this, you can just try a whole bunch of stuff, and it's pretty straightforward to do that. And if you're lucky enough to have like a chunky computer sitting in a corner somewhere at work, you just put your data on there, and you start it in the morning, and you come back tomorrow, and you read the list of the things, and you go, the right model is that. Easy, right? Okay, that is the end of my introduction to psychodrama and machine learning. Yes. Production. Okay, so that's the end of the code section. So that's like an introduction to things you might want to use. Like if you had to start like an analytics thing or a machine learning Python tomorrow, they're probably the tools you want to use. So the next question is like, okay, say you've built the cool thing, right? Like you have this data set and you learn how to predict, I don't know, like the right thing to show to a customer when they come to your website or something like that. And it's a cool model, and you show your boss, and your boss is like, that's a cool model. And then products see it, and they're like, that's a cool model, we need to make that a product, and put it in the website. And you're like, shit, how do I scale this? Like, how do I make my thing that I just made on my computer with some hacky code run somewhere else for thousands of requests or something like that? Luckily with Python is foremost, aside from the awesome data stack it has, actually most people are using it for web development, right? So you get all of this stuff, right? So functional analysis, we talked about pandas, there's SciPy, which gives you like statistical things. There's beautiful soup, which knows how to talk to HTML and get all the important things out of it. Visualization, you've got Anaconda, despite the terrible name, is really good. Seaborn, which makes maps plotted pretty. Bokeh, which is plots to something like D3.js. So you can make plots that are interactive, right, in a web browser, right? They're JavaScript, so you can zoom in, zoom out, all that sort of fun stuff. You so if the only reason you're still using R is ggplot2, you can really let's start using R. Model building, scikit-learn, stats models. There's a bunch of other things. There's if you're into deep learning, because deep learning is a buzzword, and everyone should follow buzzwords. There's a thing called Python 2 that's coming out of the lab in Canada. Anyway, so this does like all of the neural network things that you might have heard about, and all these fancy articles tell you how good Google is at doing neural networks. Right? All of those things are implemented. Knows how to do derivatives magically without you having to tell how to do it. It does stuff. It's very exciting. You should look that up as well. Serving results models, right? So once you have your thing, you can stick it behind a web server. There's many different web servers in Python. Some of the popular ones, Flask, Django, Tornado, they're all sort of like production-ready web environments that you get for free. You don't have to change languages because they're already there because people are building this stuff in this language as well. And then there's testing. There's a whole bunch of testing stuff. PyTest, PyUnit, nodes, to name a few. Testing is important. I found this very illustrative with Jenga diagram. If this was all of the stuff that you do with your data, or all of the stuff in your product, right? Data is this one lonely little Jenga bit down the bottom there, right? And if your data's shit, everything comes tumbling down, right? My professor used to say shit in, shit out, and that is like best thing to remember with data. You want to make sure it's clean, you want to make sure it works. Because when you build a data pipeline, it's very difficult to know if it's going wrong, right? You build a website, and you expect to click on a button and something happens, right? You click on the button and that thing doesn't happen, it's very obvious. You build a data pipeline and something breaks, well, often you don't really know because you don't know what the expected result was anyway, right? And this will stop you going to your CFO and saying, look, we got a 40% increase in this thing, and then coming back the next day and going, sorry, it was a bug. It's important to have testing in your data pipeline, especially data pipelines. The libraries I was talking about before, they're all very well tested, right? And if you want to contribute to them, you have to contribute tests and documentation. Okay, scaling. Spark. Spark is a thing people have probably heard about, even if they don't know what it is. It's like the new Hadoop, it's going to change the world, it's big data, right? Spark has a native API for Python. So if you want to use Spark and you want to be 100 times faster than Hadoop, which is what all the advertising says, Python is the place to be because you get your data stack, you get all of those cool things, and you can tell Spark what to do as well. On top of that, we saw scikit-learn knows how to use multiple cores. IPython, which is like an interactive Python environment, not only knows how to use multiple cores, but knows how to start them up on multiple machines over a network and send stuff to them, right? So when you're at work and everyone's gone home and they've left their computers on and you want to run some stuff, IPython is your friend, right? You just send workers out to all of their machines and use them. It's like a very important concept. Okay, so we get all of those things. The last thing I wanted to talk about is collaborating. I think it's really important. So a lot of the time, I think maybe sometimes you forget when you're used to talking about data things, people know about data stuff, and you're like, you spot a hold of this jargon, and then you go and talk to someone who has no idea what you're talking about, and they just look at you blankly as you're trying to explain the things you did and why it's so magical that it's an important thing. Right? It's a very difficult communication barrier, and if you want to be able to collaborate with other people, you need to be able to explain the stuff you did and why it's important. IPython has what's called IPython notebooks, which unfortunately I think is also now available for R, but don't tell anyone. So it looks like this, right? It's a mix of Markdown and a REPL, like somewhere where you can enter and execute code. So what you end up with is like a notebook where you can put in LaTeX, you can put in Markdown, you can put in links, you basically build a website, but you also embed in that the actual code that does the stuff. So you can save all of that as a document, and you can show that to people and say, this is not only the results I got, but here's how I got it, and you can read it as a story. We use this at work, and it's been pretty cool to see people who don't have a data background pick up this sort of stuff and look at the things that other people have done and go, that's pretty cool analysis, and if I just change this little bit here, I can run it for the data that I've got and see cool things, right? And so it's a really good way of being able to share like data stories and get people to actually like learn how to use this sort of stuff. Actually, these slides, or iPad, magic, right? It knows how to do slides as well. So this is a notebook, which is all the things I just showed you, and you can magically turn that into slides as well, which holds this thing using reveal. Brings me to my last really important. We're hiring. We have a data team in Melbourne. Well, actually, our data team is split between Melbourne and San Francisco. So, first thing is if you join the data team, you get to go to San Francisco at some point. It's kind of nice there. They've got next to us. It's cool. We're looking for a front-end engineer, a data engineer, and a test engineer. But mostly, if you saw the talk last week, we're looking for data craftspeople, right? Like people who are interested in like leading on these sorts of things, but also learning our full stack, teaching people who don't know much about data analysis how to do data analysis, and at the same time learning from people who know how to build awesome web stuff, how to do that. So we've got like a team that can pick up anything and do stuff. We get to build cool data products and see it from inception, where we're like, that's a really nice idea, and I made a graph to prove it, to we've put it in the product and people are using that stuff now, right? So you get to do the full thing. So if you're interested, I'm going to put the thing up on the website, but you can either come and see me, or you can email that thing, or like respond to the forum. That's it. Now let's start. Thanks,
Chris. So, basically got 5 minutes till we're officially out of here, so just a few housekeeping rules. If you could drop any beer bottles in that big wheelie bin, put the pizza boxes in a big pile here, that'll kind of help us get out of here quick.